Hi. Welcome to the Swift on the Fast Rails presentation. My name is Marcin Krzyzanowski. I'm very active on Twitter, so you can find me there. I have a website where you can find pronunciation of my last name. And I have a GitHub account where, look, there's Natalie. You would know that. So I have three projects. That's a major project of mine. CryptoSwift is a implementation of cryptography algorithms in pure Swift. And this is the project that this talk was based for. Objective PGP is an implementation of a pretty good privacy protocol, if you're familiar with that. I work for PSPDFKit. Does anyone ever heard about PSPDFKit? Yes. Oh, I have to make a photo for Peter. Really? Yeah. Can you again? Awesome. Yeah. Okay. So we build a PDF framework for iOS. We started as iOS, and now we have Android and web version. It's the best PDF framework on the market. Also, we have a PDF viewer. This is a free application available for iOS and Android. You can download it from the Google Store and App Store. It's like a preview of our framework with this full-featured application. I have a question for you and ask for the favor. I know that Peter Steinberger, who is my boss, is very active on Twitter. And I will show a slide. And if you have a Twitter account, just make a photo and tweet it. And add Peter, okay? It's taped. I will stay like this. Yeah? It will justify my being here today. Okay. Thank you. Now we can start with the talk. In 2014, Apple got us by a surprise and announced a Swift language. I remember that day. I couldn't sleep after the announcement, but yeah, that was like a few years ago. During that presentation, they show us this slide. On this slide, they pretend how fast the Swift is comparing to other languages. So they show a Python. I don't know who uses Python. Like for iOS development. I know, but yeah. Okay, but that's the base. Normally, the C language is a base for the performance benchmarking, but yeah, we use Python. And there is Objective-C. That is faster than Python. And Swift is even faster. It's almost 4 times faster than Python. Of course, if we just look at the difference between Objective-C and Swift, it's just 1.4. That is not that big value. But why Swift? Why did we get a Swift at all? So at some point, Apple felt that they need to give us a better tool, better language. And they asked themselves, can we improve Objective-C so that we will stay with Objective-C? And the internal answer to that question was no. So they started think about new language. Fun fact, ARC, automatic reference counting, is it happens because of Swift. In 2010, when we got this into Objective-C, it was already designed with Swift in mind. And at that time, Chris Lattner already started designing Swift. So we got it as an addition to the Objective-C, but this is now the internal part of the Swift, and we actually love it. Why Swift? Well, Swift is, of course, designed as a better language, more secure, where the memory is more, constrained. So I found this nice quote. I changed it to Objective-C, but it was about C. A C program is like a fast dance on a newly waxed dance floor by a people carrying razors. And Yeah, that may happen. And I don't know who Valdi Ravens is. I tried to Google, but is he it? Yeah. Okay. So yeah, we have a Swift. If we have a Swift already installed on our machine, we can use it like a script language, so like a Python. Think about it. One way is just to type Swift, and we have a rep, and yeah, just DevFest Baltics, print DevFest Baltics is the first mobile conference in the Baltics, and print the output. Or we can create the file, like a bash file, like a Ruby file, with a header, and put the code below. So that will be executed as a Swift, as a script Swift. I'm sorry. Yeah, you can stand. I'm sorry. It's sometimes the information on the bottom. The problem with that kind of invocation of Swift is that it's very slow. First, it's unoptimized. Well, basically, it is unoptimized, and this is the main reason. For what I saw, it's like 1,000 times slower than the compiled code. I got this. I tried this approach with a Natalie project that you failed on the test, and it started like a script file, and it was significantly slower than when I switched to the build version. By the way, Natalie project it parses storyboards and generates some code between the storyboards and your application. So it was very slow. So I switched to build Swift, and yeah, it was very, very improved. And we have a compiled Swift. So this is the Swift we use and we know. Compiled Swift pros is optimized, yeah, like any compile language can be. But the cons is build times. Let's consider this sample. This very simple sample. We have an array of integers, and I add 6 arrays of integers, one to another. And unfortunately, this expression is too complex to be solved in reasonable time on this machine, and this is 2015 maxed MacBook Pro. There was another example with adding strings, but they eventually fixed that. Although, yeah, we have that kind of problems, and it's very painful. Another example, just recently, in a CryptoSwift project, I noticed that, well, something happened, and it built way too long. So I started debug and found that one function compiled for 60 seconds, right? What the hell, right? 60 seconds, just one function. So I look inside, and that was the fix. The fix was to replace plus with advanced by, and to remove there's bit shifting operations here. And now it compiles like, yeah, less than a second. So this is the problem. We have to struggle with the Swift every day. And the reason why this is that slow is how the Swift protocols and integers are implemented. Now we have a more generic implementation of Swift, so to resolve the type, it takes a lot of time to compiler to resolve the time to find the matched functions, etc. And we see the results. It's not that great. How the Swift is compiled. You may be familiar with that, so I will go quickly. We have a source code that is parsed, changed to abstract source tree representation. Then this tree is Swift intermediate language representation is it's a text, still text representation, but changed our source code. And then we go to the LLVM stack, and eventually at the end we have object or executable file. This Swift intermediate language part was added to LLVM chain especially for Swift. Why? Because Swift is a language that has some abstraction, and LLVM by itself is not able to optimize this abstraction in a good way. So CIL is the layer that optimizes Swift abstraction. When we compile, we have a few settings we can use to speed up the code in the runtime. Most basic Swift optimization level. This is from the Xcode perspective, but it all has command line equivalents, so it can be built from the command line. Optimization, 3 values. Known, red is not good. Known is usually used for debug. I don't use it for debug here, but normally this setting is for debug. No optimization. It's slow, okay? It's very, very slow. Release. For release, we either use -O, which is fast, or -O minus whole module optimization, and this is way better for the whole modules. Do you know what a whole module optimization is? You know? No? Okay, there's a blog post on Swift.org that describe the whole module optimization, how it works in details, so I won't go into details. The thing is, normally, when the code is compiled, the compiler sees just one file. So he can optimize only in the scope of one file. With the whole module optimization, it starts to see other files and can take that into account during the optimization. So it's benefit for all these loops that optimize code. With whole module optimization, whole module is optimized at once. Well, incrementally, but it doesn't matter. Next setting, disables safety checks. I use that. You don't have to use that. I use it because it helps. Swift is written with a safety in mind, but you can disable some of the checks. That will result in a faster code because there's small code, just less code to execute. Some checks like overflow or something is just not executed. Just assume it works. This is my setup. Yeah, so I have checks for debug and disable it for the release tests. This is the new one, set up for Swift 4. It's a first part of memory ownership. There's a manifesto available in Swift repository about the memory ownership, and this setup is about checking the access to the memory. Basically, what can we do with this setting? We have a full check. Full check is static check during the compilation and runtime check. This is a full. We can choose just a compile time check or nothing. I use a compile time because I don't want anything during the runtime. So I use with the just static checks, although by default is, I think, full enforcement. No. This is maybe not obvious, but having debug symbols may affect the optimizer to not optimize some code. The thing is, But this is old thing, and it was in GCC, as you can see. GCC have additional switch to care about it. The thing is, let's say you have a code, and during the optimization, compiler decide to just delete one variable, right? Because it's not used or something. Due to optimization, it shouldn't be there. But when you debug it, well, you expect that variable in your code, right? So the symbol has to be there. So if there is a symbol, it cannot be optimized out. So there are missing opportunities to optimization. I know, but that's the fact. In source, there's a small things. This ampersand plus minus multiplication versions of normal plus minus operations is unchecked operations. Unchecked plus and unchecked minus. Basically, like we had set up to globally disable checks, we can just use this version of operators to disable checks for that operation. When you can use that? If you have a loop that is executed 1,000 times, and you have a lot of addition, this will speed up like by 5 to 10%. And yeah, if you're doing a micro improvements, it's significant. There are other like functions you can use that are faster versions of normal function. This init truncating, if needed, is an initializer from integer. When you initialize one integer with another, normally there will be checks for overflow, how many bits, how long, and so. But you can just go with the truncating if needed. There's a fast path that will just copy bits, and it's that fast. It translates to one operation in LLVM that translates probably to one operation in assembly at the end. Normally, with the checks, there's more to. The same with truncating bit pattern. It's no longer available. Yeah. And they use it in the standard library. They use it a lot. Another thing is inout. You know what an inout, this attribute is? Who use Swift in your current project now? Okay, you know what an inout is. Yeah, this is from programming language, this book. Inout parameter has a value that is passed into the function, is modified by the function, and is passed back out to the function to replace the original value. So the thing is, that should work like this. You pass the value, it is copied inside, you work on a copy, and at the end, the value of the copy replaces the original value. That's how it should be, but it's optimized. It's optimized like pass by reference. So you actually inside the function you work on the value that was passed to as a parameter. This is the example. I quote Chris Adolph here. During the break and refactored a parser combinator library to use inout instead of returning, and it's 5 times as fast. And it's fine. It works like this. I change a lot of code to use that. You have to be careful when you change the code. You have to be sure, because you have no checks, right? You have to be sure you're on a single thread. It's not used by any other code at the same time and so on. But if you have that kind of function, yeah, it's fine. It's done fast. Some obvious optimizations. Struct over class. Well, the struct is faster by design. The struct is just there's just bits or bytes of data in the memory, while class has to look at this witness table and all that stuff, check if there's inheritance. Like there's more happening during the call. final class. Final class is, this is the final attribute for class means, okay, this is the class that has no subclasses, right, in this module. Like, it cannot be subclassed. Then, compiler can get that into account and well, apply additional optimization by not checking some conditions. And private final class, actually I could write private class without final, because if we have private or file private, the compiler will figure out by himself if the class is final or not. So, you know, with a file private attribute, we just work with a single file. So we know if there is subclass or not, because if it is in this file, okay, there's a subclass. If it's not, the class is final, right? Compilator can check that. Now, I think there's one non-obvious example of optimization. Simple code. There's a counter, 4 millions array of 4 million bytes, limit is equal to count, and loop that add some value. This execute on that machine in 2.7 seconds in release mode build, so it optimized. Does any one of you have an idea? There's a one-line change that make it fast. That's just a guess, something.
Unsigned integer?
Yeah, very close. Look. You see that change? So if I make it int, it's just 1.2 seconds. It's twice as fast, right? It's very non-obvious. This is because, well, in Swift, everywhere integer is favorite type, and sometimes it's just not optimized. But that's something we cannot overcome. This is just, you can argue with that, but in a source, like for loops, the old good for loops over maps are easier to optimize. So it will probably result in just faster runtime. The same to reduce. And I have a example. This is the version of code with the reduce. It is extension. The point is change the value of the directory values multiplied by 5, right? So there's I have some dictionary, reduce, right, and call that function to do the change. It's very Swifty, and it's very nice. I can do the same with a for loop. Also, I have some transform helper function, and I call it, and I change the value and multiply by 5 here. But this time, the other one was executed 0.9 seconds, right? And this one is 0.8. And this is a very small example, because there's just two values in the dictionary. That will probably be more visible in a bigger dictionary. Do you know what an inlining is? Yeah. Who knows the C? Like, okay. You want to say what an inlining is?
It's when an optimization step code is putting inside some function instead of call this function like using stack and etc. etc.
Yeah, exactly. Instead of call the function, we get the body of the function and put it in our code we have here. What's the benefits? First, call to function. That always takes something. You have to find the address and so on. You have a stack, right? Well, stack is cheap, but I want to see this. Yeah, and the other one is if you call function, you cannot optimize the body of that function because it's a separate function, right? Well, of course, the compilers are not that dumb and they can look to the function, but normally not. If you have that code in your code, it's just one block, so it can look on the whole context, and optimization is way easier. So you can optimize the body of another function in your function. So that's inlining, and in Swift we do have inlining. Inlining is very used in C, but we do have inlining. It happens automatically on the CIL level and LLVM level later. But we can ask the compiler to do the inlining if we think that that's the good idea. But we use the private attributes. First is at inline always. It's a hint to compiler to, okay, this function should be inline. If that doesn't work, you can use transparent. That means, okay, no matter what, these have to be inlined. And it will be inlined during the compilation. Yeah, this is not available, I think, now, but there will be public version of inlineable. But you can find it if you read the source of standard library. There's a lot of inline function or the functions that are marked to be inline now or in the future. There's a problem with inlining, though. Now we don't have that problem because we don't have an ABI. It's not much a problem. But if this function, let's say this is the function from the library, right, or the other file, goes to your code, and that function will change, what do you have to do? Well, you have to recompile everything. This and this. Well, this not. This. Whenever it was put in, it has to be recompiled. Otherwise, it will execute the old version of your function, right? So it's no longer just jump and execute new version. You have to recompile your source to get that code into your code, and yeah, that's the only thing. Now let's talk about memory. I use that to, this is the array of bytes. Unsigned integer 8, it's a byte. This is how I build a block of chunk of the memory. And so I have a memory, I have an array of some memory, and I change the fifth element to 128, right? But what if I won't use the standard library and standard arrays, so the thing we have with a language? I can go with a raw memory, the old school, a C way of dealing with the memory. It's unsafe, of course. It will be unsafe, unsafe something. So I create a buffer, allocate it, use it, and deallocate it. Why do I do that? When I modify the bytes inside that block, normally it will cause the copying of the array. The bigger arrays, longer will take, because the copy, 1 megabytes each time in the loop, that will take a time. But with my buffer, well, I just modify and nothing happens, because there's no automatic, no code, copy and write, right? it's up to me what is going on with the value. Of course, you have to be careful because it's no longer semantic of array and so on, but it's fast. So the version, this is the same, this gives me the same interface, almost. I allocate the buffer, initialize the buffer, change the fifth element, deinitialize, deallocate. Once I do, normally, like in my case, I have a loop somewhere here, and I work on that buffer. And after I'm done, that should be, of course, like somewhere here, I can create the array again from the bytes, raw bytes. And this is very fast, very damn fast, comparing to work with a value type array. And look, two notes that just initializing array of bytes is 10% slower comparing to allocating the same amount chunk of memory. Now, do you remember something from this study, how the memory is organized in a process? Like, yeah.
You like that?
Sorry?
Like that?
Yeah. Yeah, exactly. So we have a stack that grows from the top to bottom. We have a heap that grows from bottom to top. There's a free space. We have some static data, instruction detailers. Static data can be created by the compiler, right? If we have static values, it will probably go somewhere here. So it's part of our executable. But anyway, we have a stack and a heap. You know what I want to say? Stack allocation is fast. Why it is fast? Because to allocate stack, we just change the value of register, right? And that's all. We have more memory we can use on stack. But a heap, well, yeah, it's not that easy. We get probably a page of the memory. We have to care about deletions and all that stuff. Well, it's more complicated to allocate a chunk of the memory than stack. So the stack allocation is very fast, and a heap allocation comparing is slow. Of course, it's faster than SSD or something like a hard drive. But yeah, comparing it's slower. So what can we do with the Swift code to make heap allocated values a bit more efficient? One of the techniques is pre-allocation. Pre-allocation works like this. You have an array and you say, okay, I will use 1 kilobyte here, like 1 kilobyte, and this is what I need. So internally, it is allocated at the time, but still count is 0, everything is 0, you can append the values. So what's the benefit? The benefit, whenever you do append, call the append, it won't allocate more memory if needed, because you already have that memory, right? You already prepare the variable to work with that chunk of memory. Normally that would happen, okay, I have an array, there's like something is pre-allocated like a few bytes, and you append, so it allocate more, and this allocating, I don't know how it's implemented in Swift, some kind of reallocate, but let's say, is expensive. This way, we just can avoid that. And no quiz.
But if your mistake, you will need more memory, it will be crashed.
No. It will grow. Oops. It will grow, of course, and it will reallocate and all that stuff. But if you know already up front, well, to that point, it will be fast because it's there. Okay, there's a quiz, like 3 questions. No app, sorry. Okay. Array alloc. Yeah, we have array. It's array with the one element 0, I append -1 and append 1. So the question is where the array will be allocated, on the stack or on the heap. There's only two choices, so you know.
It's a hard choice.
Yeah, just guess, you got 50 chance. Okay, does anyone think different? Okay, that will be on a stack. Yeah, why? Well, everything is happening in the same stack frame. Array is here, so it's small, so there's no need to go to the heap. And we can check that in the debugger. You can check a value of register RSP, like just reading this register, or with frame variable, you can write, you can print the current stack frame variables, right? So I see where is the stack, it's some value, and all the value are close to that, so it's probably stack. Now, it's the same code, but one modification, this append happens in dispatch queue async, so asynchronously, where the array will be allocated. Yeah, it was easy, right? What if not? What if not? Yeah, it's on a heap. It's on a heap. You can see this value is significantly different. So it goes from the bottom somewhere. Has to be a heap. Why? Because array will live way longer than this function lives. So it cannot stay on the stack here. The function will gone, and the value will stay. So it's on a heap. And whoever told you that, oh, I shouldn't say that. Okay, we have a struct. It's similar to the previous one, but it's with a struct. You know, the struct is value. What will happen? Where the struct will be allocated in this example? So we have a struct and asynchronously perform some operation on the struct.
Stack.
What?
Stack.
Stack?
Stack.
Okay, let's see. I don't know. No, it's heap. Oh, sorry. That was close. Yeah, the point is, whoever told you that the struct is always allocated on stack is not true. Stack is allocated. Struct is allocated whenever it is right to allocate struct. So if it's called like here, it's the same rule like for the array. It cannot be allocated on stack because it's async, so it has to be on a heap. If we had a closure that is already executed on a heap, everything inside will be allocated on heap.
What would happen if we will first call sperform on the main queue? Like?
Yeah, that's fine, because I don't need a S any longer. So it stays on stack, right? Here. Like without this, right?
Yeah.
Yeah, that will be on stack. The same like with the array. Here. Really, the same like a rule. Know this code, so everything, any use of struct is inside this function, so it can operate the frame of the stack, and yeah, it can be on stack, simply. Generics. You know what a generics is, right? Yeah. Generic code enables you to write flexible, reusable functions and types that can work with any type and are subject to requirements that you define. That they are the constraints. Yeah, who knows? I don't know where I get it from. If you wonder, some of you wonder how the generics may look, this is the real world example. I got it once. It was generated when I was dealing with the generics. Yeah, it's very, very, very beautiful. But when it comes to the performance, I have this example. This is an example from, I'm not sure, it may be in this book, Swift programming language, or in the repository. Doesn't matter. What do we have here? We have some protocols extension, and we have a class that is generic, so type pingable, and we have a function that is doing something in a loop, right, called ping. What this 10 means? Yeah. Okay, I'm almost over. And this is executed in runtime on this machine, 0.2 seconds, right? And there's one change that can make it blood fast. I don't know if you notice, I added specialization. I mentioned about the specialization on the previous slide. I added specialization that T is int. And yeah, just nothing else. And now let's execute, see, 0.06 s. Just by adding the specialization. Normally, the compiler specializes the generic function by itself, but sometimes you have to help him. And this is the kind of help you can use. And it has a very big impact on the performance. With the generics, there is a problem. The compiler can specialize generic functions inside the module. So if you have a library that the API is generic, uses some generic types, it won't be specialized in the code, in the application that use that library. An unspecialized version is very slow. This is why some time ago I completely get rid of the generic API and just go with the repeating a code for the most used types, because that way I get the versions of the functions that are specialized for the type I need. Normally, the generic is very slow. I can show how it works. This is hardcore. This is SEAL, a Swift intermediate language. The one I show you that was added to the Swift. The code we just saw with a version, this is the version of that code without the specialization, bb0 block, and it there's something and call the function. Now, I specialize, and what happened? First, that unspecialized version become bb1, and there's something new here. And that new is the entry point, and there's the decision. If we have a specialized version of the function, just execute it. And this is the specialized version. If not, go with the default implementation, and this implementation, it has to find the layout, the memory layout of the types in the runtime. It's slow, but this is the specialized version, and it has unchecked cast game t to game integer. And since the compiler already know all the layout of the integer, he can create longer but more efficient version of that code, and make it just fast. Specialization happens automatically when it may happen. So excluding the between models, in the same module. Otherwise, you can use the specialize. It's effectively it will. It will just make a code bigger, because each specialized version of your function will be added to code, but faster. The whole module optimization won't help, because it will only be specialized in the same module. Recap. Debug is slow. It's really slow. So if you have a come to my repository and you run the tests and it will be in debug and you say, oh, it's fucking slow, well, it's because of debug. Debug is really slow, and if you ever have performance tests, remember, do not run it with a debug build. Pre-allocate memory to avoid the allocations. Stack, if you can, if you get what's going on, think or build that way so you can use the stack performance. Copy is bad. Like copy operation, copy memory is always bad. Like no, it's not bad, it's very good, but it's slow. It's just bad for the performance. And yeah, the generics, use it carefully. Think about this limitation of the between module specification. And from my perspective, less Swift is faster Swift. Okay. Thank you.